All right, well, thanks for coming this afternoon, everybody. My name's Bob Steagall, and I'm here to talk about APIs and sort of the business aspect of APIs. When I submitted the abstract for this and it was eventually accepted, I was actually a little bit surprised because this is not a talk about C++ per se. This is more a talk about the business of C++, or at least the business of having and maintaining and dealing with an API. And I'll warn you, there's lots of opinion here, and since I'm standing up here, my opinion will be correct. So let's start out on a happy thought, software failures. January 2018, Tricentis, a company that makes software testing tools, published their annual Software Fail Watch. And they found that in the calendar year 2017, 3.6 billion people across the world were affected by software failures, and approximately $1.7 trillion in lost revenue. Software failures accounted for quite a bit of downtime, not only in the United States, but other countries around the world, and that the number of software failures that were reported were about 10% higher in 2017 than they were in 2016. Interestingly enough, retail and consumer technology industries experienced the most software failures of any industry that they analyzed. I guess I can see retail. I'm not sure I understand why consumer technology, but that's what they found. Let's look at some other happy things, expensive software failures. The Ariane 5 exploded on its launch in 1996, cost $370 million. Ultimately, in one line, the cause of the failure was a double to int16 conversion. Apparently there was some quantity that accumulated during flight time, and not too far into the flight, the precision required to represent that quantity exceeded that a 16-bit integer could carry. The Mars Climate Orbiter burns up, attempting to land on Mars. Cost $235 million just to build the thing and launch it. Ultimately, in one line, the cause of the failure was an imperial to metric units conversion. A few years ago, Knight Capital lost $460 million in 45 minutes due to automated trading. And in one line, the cause of the failure was dead code that was left in a program and a test flag that was left enabled. The test flag apparently caused the program to execute trades as rapidly as possible because they wanted to do the testing quickly. Apparently somebody forgot to turn the flag off, went into production, and lots of money was lost very quickly. The late 80s, a machine called the Therac 25 caused the death of a patient due to an extreme overdose of X-ray radiation. And in one line, it was a race condition that caused this. Multiple processes trying to write to the same variable at the same time. Looking at these, certainly the second one, maybe the first, you can look at them and say, that was probably an API problem at fault. But I can't help wondering how many of these problems are caused by API failures. Even if it's 10% of the cost, that's still quite a lot of money. So I'll warn you, there's lots of unsupported opinion and unjustified conjecture ahead. And this talk is based on my experience over the past 20 years or so, building libraries and working mostly in small and medium-sized businesses. So let's think about what an interface is. Every presentation should begin with a definition from that wellspring of all human knowledge, Wikipedia. And so Wikipedia tells us that in computing, an interface is a shared boundary across which two or more separate components of a computer system exchange information. The exchange can be between software, computer hardware, peripheral devices, humans, and combinations of these things. Alternatively, you can think of an interface as being a well-defined location for information exchange. So what is an API? Well, We're all familiar with the definition that an API is an application programming interface. And we like to think of it as a set of clearly defined methods of communication between components. Another way of looking at it is that an API represents a contract between a component and the users of that component. In other words, it's a precise and complete specification of guaranteed user-visible behavior that excludes implementation detail. The API specifies the behavior that's expected by both parties. The library is supposed to follow the rules on the implementer side of the contract, and the developer is supposed to follow the rules on the user side of the contract. We all know APIs can have multiple implementations. Consider the standard C++ library. The standard itself is purely a specification if you read through it. It's lots of verbose text, but effectively what it tells you is what the interface is and what the expected behavior of each component of the interface is supposed to be. And then, of course, we have various entities that implement that interface, the major compiler vendors and anyone that has their own STL implementation. And of course, we have a number of similarly domain-specific libraries. If anyone's ever worked in the room has ever worked in medical imaging, you're almost certainly aware of a standard for medical image transfer called DICOM, Digital Image Communication in Medicine. And DICOM is similar to our standard library specification in that it specifies how medical imaging information is to be transferred from one place in the world to another place in the world. So in C++, like so many other things, the terms API and interface are normally very highly overloaded. People refer to them both as meaning the public interface that's exported by a library, or the public interface exported by a module or a subsystem, or the public and protected interfaces provided by a class, or the collection of function signatures from an overload resolution set, the interface from a collection of ordinary functions, the signature of a single function or macro or messaging protocols, and so on and so on and so on. People conflate the terms API and interface to mean any and all of these things all of the time. So for the purposes of this talk, when I say API, what I mean specifically is the non-private interface that's exported by a library or a framework as expressed in its headers, its source, executables, and its documentation. And likewise, for the purpose of the talk, when I say interface, I mean a discrete and well-defined subset of an API. Some small portion of it, like a set of functions or constants or variables or the interface of a single class. So why do people use or create APIs? Well, ultimately, we're hoping for higher quality code. This is what we get when we use a good API. A good API hides implementation details. It supports implementation change and optimization, promotes modularity, reduces duplication, removes the assumptions that we as programmers need to make when we're writing code. We can assume, if it's a good API, we can assume it works correctly and it fulfills the contract that it says that it's going to fulfill. It can help increase the longevity of our products, promote code reuse, promote parallel development, and promote better products. This is all very much common sense, no surprises here. Why would we not want to use an API? Well, there could be a domain mismatch. Perhaps an API that you're considering using doesn't quite solve your problem, or it does so in an awkward way. Maybe there's little or no documentation, meaning that understanding the API and how to use it becomes an expensive proposition. Maybe it has closed or proprietary source code, and because of this, you can't get quick reaction to problems when they arise with your API. Maybe there are license restrictions. The API's license requirements may not conform to your requirements. You know, the canonical example here is if you need to use something that's GPL, but you want to put it in a closed product. There's an impedance mismatch there that's pretty much unresolvable. It could be that it doesn't meet your requirements. It's incorrect or it's inefficient. There's poor support. works on the wrong platform, wrong compilers. Maybe the vendor of the API just has a bad reputation. You don't want to deal with them. Well, creating an API is different than building an application. An API is something that's built for developers. And it may surprise you. I know it surprised me when I learned this, but developers are not ordinary users. Multiple products can or will share a given API, and useful APIs really tend to have a long life. Look at the STL. The STL is now 25 years old. I can remember many years ago when it was first released from HP Labs, and one had to go to an FTP site and manually type in FTP blah, blah, blah to download it. Backward compatibility is usually a high priority. If you're writing an API, breaking changes have to be carefully considered and managed. And likewise, robust change control is absolutely critical to maintaining product quality and your sanity and the sanity of your users. APIs have unique maintenance challenges. I think that good documentation for an API is extremely important, probably one of the top 3 most important things. I also believe that extensive testing, preferably automated testing, is extremely important. Creating an API is more dangerous than building an application because APIs have a multiplier effect. So how do we talk about APIs in the context of a business, and how do we value them? These are difficult questions. I don't think anyone really has a succinct and easy to apply answer. But let's think about the quality of APIs. Why are so many of them so awful, right? Well, I think these questions are actually a little easier to answer. Bad APIs are easy. They're easy to build. For every right way to do something, there's a lot more wrong ways to do it, and statistically, probably more likely to implement the wrong ways than the right ways. The wrong way is inevitably easier and faster. It's inevitably less expensive to create in terms of dollars and time, and often represents the path of least resistance to some intermediate short-term notion of what success is. On the other side of the coin, building good APIs is a very difficult thing to do. Finding the right way to do something is often very time-consuming. I remember solving a particular problem having to do with functional magnetic resonance imaging, company I worked in several years ago. And I spent about 6 weeks with a whiteboard and marker and pad of paper and pencil to solve a mathematical problem, which I eventually implemented in code. And I was very lucky that I had a manager at the time who let me actually think instead of demanding that I make noise by pounding on keys on my keyboard. But I spent 6 weeks not writing any code, but just simply doing math to solve the problem I needed to solve to meet a requirement that was set out to us by our customer. The right way is usually more expensive to build because, again, costs more dollars, takes more time. It's more unpredictable, especially if you're building something from scratch. Greenfield development is difficult and unpredictable. And I find, in my experience, and perhaps yours is similar, building a good API because of the previous factors makes it substantially more subject to managerial skepticism or managerial disdain. I remember being in a meeting with a sister department in a company I worked at, and I was there to propose that this other department in our organization begin using some code that we had written because it seemed like it would solve their problem. And they actually wanted to do that. And at the meeting was one of our head sales guys at the company who was pretty well respected and a very successful salesman. And the owner of the company came in and the sales guy said, "Why are you engineers always trying to write stuff from scratch?" And of course, that was all she wrote. Nothing happened after that because of the bad connotation that we're just wasting time and money. Let's talk about technical debt. We've probably all heard of technical debt. Well, what is it? It's the cost of additional work, rework, caused by taking shortcuts now, or at least this is the definition these days. The cost of additional future rework from taking the easy way out now instead of a better solution that could take longer. This is the way we think of technical debt now, but the term technical debt was actually coined by a gentleman named Ward Cunningham in the early 90s. And he originally intended this to be a metaphor to capture the trade-off for short-term progress that would be repaid over the long term by refactoring. Just like you borrow money now to buy a house or to buy a car and you pay it off over time, the idea was, in his thinking, it was an analogy. I would borrow against my future technology. I would make some short-term compromises now, but I would be a good citizen and I would repay that back over time by refactoring. And ultimately, I would get to the spot that I wanted to be. Of course, in the real world, that doesn't really happen very often. So technical debt is very much like monetary debt. It tends to grow non-linearly, almost exponentially, and it accumulates interest in a sense. The interest is the cost of rework that builds up over time. One of the effects is it increases the time to add new features to your product. And eventually you get to the point where the wheels have come off the wagon and you're pulling it through the mud, and the cost of adding new features is greater than the cost of starting from scratch and doing a rewrite. And ultimately, technical debt is sort of a one-to-one relationship. It leads to software entropy. So here's a nice picture that's intended qualitatively to represent the cost of technical debt over time. I came across recently the idea of the kitchen metaphor for technical debt. Project starts out just like you have a clean kitchen. Everybody's got good intentions and work begins. But to get to the first release, you make a few compromises. A few dishes left in the sink, but you promise yourself, I'm going to clean them later, right? First release gets done. It's successful. Management says, well, we got to get the second release out soon. Well, the first set of dishes never gets done and a few more dishes pile up in your sink. But you promise yourself, we'll clean them later. A few releases later, that's what you have. Maybe I know that I've certainly experienced this. So what are the causes of technical debt? Well, I put together a list of 2 to the 4th. And these are the things that I could think of. Insufficient upfront definition, not thinking about what needs to be done before you start working. Last-minute specification changes. People change their mind near the end and you have to make crazy compromises. Pressures of business, financial pressures. Changes in business needs and business priorities. The lack of process, just ad hoc coding. Lack of understanding of the problem that you're trying to solve. Tightly coupled components, meaning it becomes difficult to make changes in small locations in the code base without having effect that spreads beyond your original intent. No testing or test suite. Little or no documentation. Little or no collaboration amongst these stakeholders that are involved in a project. Little or no version control. Not cleaning the dishes early and delaying your refactoring. Not paying attention to the standards that you're supposed to be paying attention to. Lack of ownership. Making people responsible for success but not giving them ownership of it when they succeed. Poor technical leadership. Having people in charge making bad decisions regarding technology. Poor business leadership. These are things that I've experienced in my career. So let's talk about the result of technical debt, software entropy. In 1992, Ivar Jakobsen published a book called Object-Oriented Software Engineering, a use case-driven approach. And I think he was probably one of the first people to actually coin the idea of software entropy. And it's intended to be something analogous to the second law of thermodynamics, where disorder increases over time and there's nothing you can do with it. So he thinks and proposed that there was a similar effect in the development of software. Alternatively, an alternative definition is that over time, software becomes difficult and costly to maintain, and eventually becomes more and more complex and disorganized, and it loses its original design coherency. If you've ever read any of the works by Martin Fowler, he has another word for this. He calls it cruft. But in any event, whether you call it cruft or you pick one of these two definitions, software entropy is ultimately the introduction of disorder into the system that you're trying to build. And it's almost inevitable. It's very hard to keep it from increasing. So what are some of the symptoms of software entropy? Well, feature creep, the ongoing expansion or addition of new features that extend beyond the basic function of the product. And we're all familiar with this concept. It causes product bloat and overcomplication. It makes the scope of the product creep and usually results in cost and schedule overruns. And usually, at least in my experience, it's been caused by a desire to provide the consumer with a more desirable product without really knowing whether the consumer desires these new features. We have gold plating. I think of gold plating as being features creep on a smaller scale. And this is the addition of small features that are not part of the original product scope, small frivolous things. They also lead to fatter interfaces, product bloat, cost overruns. And because they're on a smaller scale, or at least I think of these things as being on a smaller scale, they're usually, I find, due to programmers without anything better to do, thinking that they're adding value, and they end up adding artificial value. Or perhaps they're experimenting with cool new technologies and they think, well, I want to try this new little thing, and if it works out well, it'll be this nice little feature in the product and the customers will love it. I don't know that that ever really pans out. There's the idea of brittleness, which is the increased difficulty in fixing older software. And really, it causes, at the end of the day, brittleness is the cause of very painful rework costs. And usually, I find that it's caused by algorithms that don't, work the way they're supposed to, things that, code structures and algorithms that don't correctly anticipate boundary values, dependencies that are too rigid or too cyclical amongst the components in the system, and also, in some instances, a lack of knowledge transfer from older generations of programmers, so to speak, to younger generations in the company. We have bloat. We all know what bloat is. The system gets bigger and bigger over time. Another term I think is kind of interesting and funny is bit rot, the slow deterioration of software performance over time. I think we've all are familiar with products that seem to run at exactly the same speed or slower speed over time, even though it's the same product and your hardware is twice as fast or orders of magnitude faster than it was. I can think of programs that I use which now take just as long to open on my PC as they did 25 years ago when I first bought versions of that product. And yet my PC is probably at least 2 orders of magnitude faster than that 20 megahertz 386 I bought in 1988. So that might be an example of bit rot. Let's talk about the other side of the coin, software capital. What is it? A cumulative technology that can be redeployed to newer situations. This is a term that was coined in the mid-90s by a gentleman named Dean Zaras. And there's not nearly as much written about software capital as there is about technical debt. And from what I can glean from the little bit of information that exists out there, it was intended to reflect software as an asset rather than a liability. If you know anything about accounting, technical debt is a liability. And I think Mr. Zaras was trying to approach the problem from the asset side of the general ledger. Interestingly enough, as an aside, there was a great article, I think it was in IEEE Software a few years ago, from a gentleman who posited that the generally accepted accounting principles should actually put numbers on technical debt and it should appear on the company's books in the liability. I think if that ever happened, a lot of CFOs would have heart attacks. So done correctly, software capital becomes a tool set for applications. The intent is that it raises the starting point to build new or different solutions. The idea is to reduce time to market, and it pays dividends rather than costing interest. In a sense, it is very much the opposite of technical debt. So Mr. Zaris' original idea was sort of captured in this table at the right, which I've included from his article. But the idea is there are two separate development teams, application developers and software capital developers. Application developers serve the business needs or the needs of the business units. Software capital developers provide the foundation that the application developers use. And the idea is they enhance the product quality and the developer's productivity. They promote enterprise reuse. Each side gets to leverage their strengths. The application developers presumably have more domain knowledge than the capital developers. And the capital developers are responsible for building a good, strong foundation. Here's a little diagram from his article which explains the idea that he has, that he saw. That business unit or business users would communicate their needs to application developers, who would then look to the software capital developers to jumpstart development. They would provide tools and frameworks to the application developers, who would then provide feedback, and they would iterate on that until they come to an agreement on, they've got the right technology to solve the problems. And then ultimately the application developers would deliver a solution to the business users. Now, keep in mind, this is from the mid-90s, and so this takes a more traditional or old-fashioned view of software development, and things are more stovepiped in this. Even in today's full-stack teams, though, I think this has merit. I find, at least in the full-stack teams that I've participated in, that there's naturally a division of labor amongst the team members, even if they're not specifically, I'm an application member of an application developer team, or I'm a member of a capital team. People naturally tend to fall into roles, I believe, in one of these two approaches. So here's another quick diagram intended to convey the benefits of software capital. The idea being that, yes, there's a point that building software capital is more expensive initially, but there becomes a point at which it becomes substantially less expensive than the approach where one accrues technical debt over time. So in summary, technical debt, bad. Easy to create. Software capital, good. It's difficult to create. Technical debt is cheap to create, but software capital is expensive. Technical debt is reused under the gun, but software capital is voluntarily reused. Technical debt usually has a narrow focus, whereas software capital has a wide focus. Technical debt is ugly. Software capital, not so much. Technical debt leads to incomplete solutions, whereas software capital tries to form complete solutions. Technical debt increases time to market, and software capital decreases time to market. Ultimately, technical debt increases costs in the long term, and software capital reduces costs in the long term. Okay. So why did I tell you all that? I'm telling you this in the context of building a framework for evaluating an API. This is a great quote from the book Clean Code from Bjarne. I like my code to be elegant and efficient. The logic should be straightforward to make it hard for bugs to hide. The dependencies minimal to ease maintenance. Error handling complete according to an articulated strategy. Performance close to optimal so as to not tempt people to make the code messy with unprincipled optimizations. Clean code does one thing well. Think about the adjectives in those three sentences, the bolded words. I think they all pretty much describe what we strive to achieve with software capital. And if you substitute the word APIs or libraries for code in that sentence, then this quote really nails down what we as API designers are trying to achieve. So what are the quality goals for an API? Readability. I see readability and understandability as being two different things. Readability is a necessary precondition for understandability. It is, in a sense, like syntax. Understandability is a necessary condition for minimizing costs, in my mind. It goes to the ability to understand the system that you're reviewing or that you're trying to maintain. It is, in a sense, to me, like semantics. Conceptual integrity is the quality of a system where all the concepts and their relationships with each other are applied in a consistent way throughout the system. If you've ever read The Mythical Man Month, or even not, I'm sure you've heard of conceptual integrity. Mnemonic consistency is a term that I coined. It's famous in my brain. And what I mean by it is that the idioms and patterns of usage in an interface are self-consistent and reused as much as possible. In other words, if I learn how to use one section of an API, using another part of an API should be similar. We're all familiar with things like memcopy, where you have source parameters and destination parameters. And with memcopy, your destination parameters are on the left and your source parameters are on the right. You know, you go from right to left. Whereas in the STL, typically your destination parameters are on the right and your source parameters are on the left, right? So if you mixed both forms in a given API, every time you want to use something, you might have to go look up, which form am I using, left to right or right to left, right? I think consistency, mnemonic consistency, is an important quality that good APIs have. Correctness, of course, is very important. Testability is important, and here what I mean is not only testability of the API itself, but does an API lend itself to helping make your product testable? Performance is always important, and at the end of the day, our quality goal is to, through our API, is to increase software capital. And to my way of thinking, if you fail to achieve any of the first 5 or 6 of those items, then in one way or another, you are contributing to technical debt. So how do we know if an API is good or bad? Are good and bad even reasonable or relevant adjectives to use? I struggled with this. Effective or ineffective, desirable, undesirable. At the end of the day, due to my lack of imagination, I just decided to stick with good and bad. So good, an API that mostly increases software capital, and a bad API is one that mostly increases technical debt. So another warning follows. The characterizations I'm about to show you are somewhat intuitive, but they are not orthogonal. They're not quantitative and they're not exact. To use a linear algebra analogy, I would like to give you an orthogonal set of basis vectors, but this is what you're going to get. A bad API is incomplete. It doesn't do its job. It's unstable, it's untested, or it's undocumented. One of my pet peeves about APIs is when they're undocumented. It has an inconsistent design or structure, or the naming is inconsistent. It is unnecessarily complex. It's unnecessarily difficult to learn. It's written from the perspective of the implementer. It inconveniences me, the user, to benefit the implementer. It requires repetitive boilerplate in order to be used. It's indecisive. It passes the buck. For example, it uses enumeration to specify behaviors instead of just making a decision. It unnecessarily exposes its implementation. And there are other characteristics, what we typically think of as design smells that are associated with bad APIs. Missing abstractions. Multifaceted abstractions, when an abstraction has too many responsibilities assigned to it. Deficient encapsulation, when the accessibility of members or member functions of our abstractions is more permissive than it really needs to be. Unexploited encapsulation, when client code uses type checks instead of exploiting the variation in types. Duplicate abstractions, when 2 or more different abstractions have confusingly similar names. Duplicate implementations, when 2 or more abstractions with different names have very similar implementations. Broken modularization, when data and methods that should have been localized into a single abstraction are separated and spread across multiple abstractions. Insufficient modularization, when abstractions exist that have not been completely decomposed, and a further decomposition could reduce the size or complexity. Cyclic dependencies. Unfactored hierarchies, when there's unnecessary duplication among types in a type hierarchy. Broken hierarchies. This is another big one. When the base type and its derived type conceptually don't implement an is-a or is substitutable for relationship. Cyclic hierarchies. Well, how do we characterize good APIs? They solve the problem correctly. They provide satisfactory performance. They're composed of manageable pieces that we can understand. They're built with commonly understood idioms and patterns. They make decisions, they're decisive, and don't pass the buck. They're designed from the perspective of the user. They behave consistently. They follow the principle of least surprise. They explicitly state and observe the contracts to which they will adhere. General purpose APIs, or good general purpose APIs, are policy-free. They don't dictate how things are to be used. If the context of use is wide open, then the API should leave as many choices as possible open to the user. And here I'm thinking of something like the STL. On the other side of the coin, special purpose API should be policy-rich. They should make lots of decisions for the user. And here I'm thinking of something like the DICOM APIs for transmitting medical images. A good API is stable, it's documented and tested. It behaves consistently at compile time and runtime. It has good documentation, especially with regard to error handling, has reasonable coverage and test result transparency. It's minimally complete. It doesn't overpromise what it's going to do. It uses both types of polymorphism, compile time and runtime polymorphism, wisely. It does not impose inconvenience on me, the user. It has just the right amount of convenience interfaces. It's ergonomic and easy to use. It's discoverable. It's easy to use correctly, and it's difficult to use incorrectly. It's consistent in its structure, design, and naming. And it's orthogonal mostly, although convenience interfaces tend to reduce orthogonality in interfaces. It helps the caller and the user. It provides the required extensibility. It provides robust resource management. And to the extent reasonable or necessary, it's platform independent. It's loosely coupled, modular, and layered. Coupling is by name only. Any redundancy that exists is intentionally and deliberately in place, and it's minimal. It provides manager classes, callbacks, and observers, and notifications as appropriate. It hides implementation details judiciously. It hides implementation judiciously. It adheres to all of those things we think of as being good practice and good design. So how do we get there? The next part of the talk is a simple process. I call it a simple process for API design. And it's something I've tried to use and have used with various levels of success over the last 15 years or so. And I'm hoping it may be useful to you, and you may be able to put some of these precepts to use in your day-to-day work and help you, if you are building APIs, build more effective APIs. So, if I can pontificate for a moment, here are some high-level personal principles that I try to adhere to. The 4 C's. Clarity of purpose. Understand the goals of what you're trying to do and why you're trying to achieve them. Clarity of thought. Understand the problem and understand your solutions to it. Clarity of expression. Clearly describe the problem and clearly describe your solution to others. And the 4th C, neatness counts. The presentation of your solution is just as important as the solution itself. A well-presented solution promotes understandability, and understandability is the most important thing. Understandability is the thing that reduces costs in the long run. Understandability is something that very few people, at least very few managers, seem to actually understand. On users. In general, in my experience, I see 3 categories of users, and each category has their own level of expectations. Casual users, they want ease of use, they want productivity out of the box, they want a minimal learning curve. Power users want ease of use combined with some customizability, because generally they're looking for some higher performance. Then you have your expert users who want maximum customizability. They want to solve highly specialized problems and or they're in search of the highest possible performance. If you're working on an API, I highly recommend you understand which users you are targeting with your API. I'm going to talk about process. I know process is a dirty word these days in the age of Scrum and the age of Agile, and I could rant about that for another 45 minutes, but I won't. A good process increases productivity. A good process uses objective metrics to track project status, and it helps control the complexity of the products and the projects themselves. It helps find the right tools and technology. Importantly, and in terms of coordinating the team and making sure people are not spinning their wheels, a good process helps define how, when, and by whom development activities are to be carried out. A good process helps improve the quality of your software. It uses and recommends recognized best practices. It promotes asset standardization and reuse. It enforces consistent and transparent change management. We're all familiar with the classic waterfall process. You start with requirements, you do design, you throw it down to implementation, verification, and maintenance. It's logical, it's simple, and for trivial projects, it works. But it suffers from a fatal flaw for any non-trivial product. It delays the recognition and the mitigation of risk. As the project proceeds, it becomes much more costly to correct defects from earlier phases. A requirements defect that's discovered during acceptance testing costs a lot more to fix than if it's caught in the requirements analysis phase. You know, there's the urban legend that it takes 100 times as much. I don't know if that's true. Maybe the number's higher than that. So how do you improve the waterfall process? You make it iterative and incremental. You add a subset of desired new capabilities in each iteration. You review, you adjust, you correct requirements multiple times. You correct your design multiple times. You always address your highest risk items first. You build, integrate, document consistently over the life cycle of the project. You identify and exploit opportunities for reuse. So there are several creative acts during the process. You gather and analyze requirements. You design, you refine subsets of the API. You implement, refine code for that subset. You write, refine unit tests for that subset. And please, please, make sure all your unit tests pass before you check stuff up into the master branch. You create and refine documentation for that subset. So what does the process look like? Well, it's a circle. We've all seen things like this. We begin by trying to understand the problem. We do some planning. We analyze, design, implement, test, document, evaluate, do it over and over again until we're ready to deliver a product. If I had to write this out in code, I have a class, my API, and I'm building it. I would explore and understand the problem, and while my version is incomplete, I do some planning, analyze requirements, refine my design, write some code, write and run some tests, write some docs, review and evaluate, and then, magically, I would deliver. Life is good. In reality, life is much messier than that. These things are almost always concurrent. And in fact, the code is a little more complex for the process. In the real world, the process begins by incurring costs. You explore and understand the problem, and while the costs are still acceptable and your version is incomplete, you do some planning, and then everybody goes off and does something. At the end of the iteration, you wait for people to sync up. You review and evaluate. You may do this several times until either the costs are not acceptable or the version is complete. And then you're ready to deliver. So if your costs are still acceptable and it's okay to ship, then you deliver. But if not, update your resume. If you've ever studied any sort of software engineering processes at any length, This probably reminds you very much of the unified process or Rational's version of the unified process. And I think this is really brilliant work. Along the column, you have 9 engineering disciplines. And along the top, you have the horizontal axis is time. And this reflects the real world. Near the beginning of a project, things like business modeling, requirements analysis, and design take a majority of the time. And as the product evolves, those things are still present, but their emphasis is lowered. Whereas near the end of the product, things like test and deployment, project management tend to take more time. I think this is a great idea. I think this is brilliant intellectual work. And in those few circumstances in my career when I've been able to implement this process and use it, we were actually quite successful with it. And so I recommend, if you're interested in this kind of thing, look up the unified process and read about it. I think it will convince you as to what a good idea is. And it's actually quite tailorable. So explore and understand. Understand the problem. Be able to describe it in writing and get somebody to read it. You need to understand the scope of the API. What are the aspects of the problem that you're trying to address through the API? Define the completion criteria. I don't know how many projects I've been on when we didn't really know when we were done because nobody told us what we were trying to do. Try to figure out quality metrics and targets. Define the tools and conventions you're going to use. And, spend some time thinking about your development environment. Spend some time thinking about coding standards and guidelines. Gather requirements. Functional, the old FERPS model, functional requirements, usability requirements, reliability requirements, performance requirements, supportability requirements. These are old-fashioned and boring concepts that in the age of Scrum and Agile, nobody likes to think about. I think that's crazy. Think about the teams that you've been on that do Agile and Scrum development, or at least I think about the teams that I've been on. And I wouldn't want the process that we've been using be responsible for writing the software that manages my bank account balance, or is responsible for the software that controls the PLC that lowers and raises the beryllium rods in the nuclear reactor, right? I think requirements analysis and understanding what you're trying to build is absolutely critical to the success of having a good API. I think one of the most important techniques in doing requirements analysis is just to ask questions. Here's a small list of questions of things that you could, if you were writing an API, you should ask stakeholders. And mostly it's about trying to understand the scope and boundary values of the problem. There are other questions, more detailed questions you can ask. I'm not going to go through all of them here. That you can also ask stakeholders when you're trying to figure out what is the scope of the API, what's it supposed to look like. You can use use case techniques. Use cases are a nice way to describe API behavior. They capture who does what in what sequence. They help describe requirements from the perspective of a user. Traditional requirements describe sort of a system's capabilities from a static perspective. Use cases help describe how a system interacts with the world from a dynamic perspective. To use a bad UML analogy, traditional requirements analysis are useful, but they're like static class diagrams. Use cases are more dynamic. They're like state or sequence diagrams. When you're writing your requirements, use domain terminology and try to describe things in terms of the user's language. Your requirements should be unambiguous and consistent with other requirements and complete. Don't specify the design and the requirements, and use the requirements and use cases to derive the development of test assets, another key thing that tends to get forgotten. Expect to revise the requirements many times. And don't expect to have complete or perfect requirements coverage. It never happens. It's important to review the requirements multiple times during the lifetime because they will change, they will evolve. Review is an important thing because it ensures that everyone understands what needs to be done and that everyone's expectations are in sync. Try to assess the coverage and content of your requirements and their overall quality, as well as the quality of each individual requirements. And so that's kind of where it is in the process. Refine the design. There are traditionally two kinds of design, architectural design and detailed design. I think of architectural design as creating a high-level description, and it's important for composing documentation, whereas detailed design is creating a description of individual components. In my opinion, detailed design can be useful, but often not. I tend to do more high-level design. Develop the architecture. Software architecture describes at a high level the structure of the system, top-level objects and relationships to each other. There's rarely a single right architecture. If you ask for a given problem, n architects, you're going to get k times n solutions, where k is a number greater than 1. The objective is to create an API design that meets all of your quality objectives while fulfilling the requirements and resolving conflicts. In general, you'll analyze the requirements that affect the architecture and identify and account for architectural constraints. Speaking of architectural constraints, there's always factors that constrain the resulting architecture. You have organizational constraints, environmental constraints, operational constraints, and many, but not all of the constraints come from the requirements. In building your design, try to find the key objects. Use natural language. Nouns represent objects and verbs represent functions. Adjectives and possessive nouns tend to represent attributes. Group your objects that you find by properties. Group objects that have similar properties. Try to find categories that an object either belongs to or doesn't belong, or group by behavior. Try to determine all the behaviors in the system and group them into subsystems. Derive the set of objects by finding the initiators and recipients of each behavior. Reuse architectural patterns. Just like we have component-based patterns, there are architectural patterns. There are structural patterns, distributed systems patterns, adaptable system patterns, interactive systems patterns. There are a lot of smart people that have thought about these things in the past, and these patterns exist for us to reuse in our APIs. One important aspect of these patterns is people have thought about these, and they tend to lack cyclic dependencies and other problems that lead to brittleness in the systems that we build. An important step, or at least techniques that I like to use, are scenario-based design. A lot of frameworks often service a small set of common usage scenarios, and these usage scenarios generally, the most common usage scenarios, only employ a small set of the framework. And so as you're building a framework, it's key to understand what are the most common usage scenarios and optimize those usage scenarios from the perspective of the API user. After you've identified the major nouns and verbs in the system, first write pseudocode to quickly sketch out usage. Then write real code, or I like to think of it as phony real code because there's no real code yet. But write out the code that you want your users to write. And think critically about that code and ask yourself if it makes sense. And for my money, those last 3 bullets are the most important 3 bullets in this presentation if you're going to write an API. This is what I do all the time. I don't know that I'm any great shakes at it, but it works for me. Scenario explorations can and should feed back into the design. And once you've got a design in place, you want to communicate your architecture. Documenting it is critical for understandability. It provides a roadmap for implementers if you're not the only one working on it. It helps promote peer review. Just like you have code review, you can have design review. It forms a basis for good user documentation. If you're very lucky, you'll have a good technical writer that can take your requirements documents and design documents and turn them into good documents for your users. Always try to capture the architecture and some of the rationale. Sometimes users need to understand the rationale behind the design decisions you've made so that they can use your API effectively. Agile processes, on the other hand, tend to de-emphasize documents as being passé and old-fashioned. But I think that the high-level requirements and specifications, architectural specifications, are critical. They're important enough that they need to be captured somewhere. You can capture low-level requirements in design if time and space permit, but generally I find that they're not really required. Review the design. It's important to assess the design near the end of each iteration and try to understand whether these qualities, whether the design that you've worked on, that you've formed so far, meets these qualities. Does it adhere to the specification? Is it consistent? Is it maintainable? Is it understandable? Is it traceable to requirements? Nobody thinks about traceability these days. It's quite a shame. All right, so that's where design review would occur in the process. Finally, at the end of the process, you want to evaluate and plan. You want to review the API. Does the API provide the functionality that you're promising? Has it met its quality goals by whatever quality metrics you've set out for it? Are there aspects of the API that need to be refined or changed to improve customer satisfaction? Within reason, of course. Plan for the next iteration. Is there any unfinished work that needs to be done? Are there any major requirements changes you need to account for in the coming iteration? Are there any new constraints on the project that have just been imposed? Like, oh, wait a minute, we're not shipping on Intel, we're going to ship on ARM. Maybe that could happen. What's the scope of the next iteration? Finally, I've given you some ideas. How do you fit this into your overall process? Well, you might begin by discussing your ideas with your customers and colleagues. If you can't convince them that you've got a good idea for an API, it may be time for a rethink, or maybe not. If you can convince your customers and you can convince your colleagues, then you might be on the right track. So now you need to make the business case to your manager or your management. So figure out where their pain points are and adapt your pitch according to their pain points and promise to make their life easier. Clue them into technical debt and software capital. Provide realistic estimates of your upfront costs. It can be challenging, but ultimately it's not super difficult to estimate what costs are. You can figure out what overhead are and what labor rates are. And if you have realistic estimates of time, you can sort of put together a budget for what some effort would cost. Try to understand the risks. What are the real risks of schedule slip? Cost overruns. Provide realistic estimates of benefit in terms of reduced cost or sales growth. And if you're really brave, you could do an NPV calculation and tell them, look, we're going to save this money now and it's going to result in so much money in the future, and net present value tells us we're actually making money today. But honestly, in my experience, be prepared for disappointment. Change and new things represent risk, and managers don't like risk. You can also do what I've done a few times and just do it anyways. Adapt the simple API process into your employer's process. How do you do that? Well, try to fit the iterative spirit into your company's practices. Try to create written artifacts, even if no one sees them but you and you hide them in your desk like I've done before. Try to ask the important questions at every stage in the project. Solicit feedback from your stakeholders and colleagues. Accept feedback graciously, especially negative feedback. And if you have reviewers who are difficult, then consider Crocker's rules, and I'll let you look those up. But consider the feedback carefully, and be prepared to change your mind or change direction if someone makes an important point. You have to sort of be objective, and if someone has a good point, you have to be prepared to change course and change your mind. At the same time, remember all our high-level goals of consistency, conceptual integrity, and mnemonic consistency. So, from my point, I'll end with a few recommendations. From a practical perspective, integrate continuously. Everyone says that they do this, but I've been on teams where it doesn't happen, even recent teams. Leave things better than you found them. Before merging, always make sure your unit tests pass, and the pass rate is better than or equal to that in the master branch. Always design for change. Try to anticipate the ways in which requirements might change over some appropriate time horizon, and try to build in reasonable facilities that can accommodate those changes in the future. You can't anticipate what's going to happen 10 years from now, but you might be able to anticipate what the needs are going to be a year from now or 2 years from now. And maybe in anticipating those and thinking about that, you will be able to build in hooks into your API such that you can accommodate those changes. Remember the 4 C's that I mentioned before. If you can't explain or justify what you're trying to do in a clear and concise way, consistent with the rest of the API, then just don't do it. Don't take criticism personally. People are what they are. I very strongly recommend using scenario-based design. Write pseudocode, pencil and paper. Write phony real code, pencil and paper. Finally, use your own API. The quickest way to uncover the shortcomings in your API is to use it yourself. And if it irritates you, imagine what it's going to do to others. Finally, evaluate continuously. Take these principles to heart and then frequently ask yourself, does my API exhibit any of the bad characteristics that's been listed here? Does my API exhibit any of the good characteristics? And viewed from a high level, is my API meeting the goals I've set out for myself? Am I observing the 4 C's? And that's it. Thank you.